This screen goes to show our program as it lays out for our degree. And there are some changes from what's shown in the catalog. The updates are we've simplified and reduced the number and range of courses that are necessary in order for students to complete on the ESYS courses in order to get your degree, which is a good thing. There's less confusion. We no longer have course part A, part B, part C, part D. They're just given single course numbers. And so there are 7 courses in our program. We have the ESYS 50, 51, 54, all the way up through 69. So what I encourage you to do is take a screenshot of this, take a picture with your phone or do a screenshot, and then I will also make it available as a something that you can access on Canvas as well, but having a screenshot makes this very handy for you. I might not get the information into Canvas for a day or so. So there are 7 courses. They are described as such, and then I'll show you next semester's schedule to show you which of these courses will be available to you for next semester. Any questions on these so far? Okay, let's go ahead and look at the next document that I'd like to share with you, and that will be what's coming up for next semester. So let me look at that under Chabot. And in Chabot will be here. Let me go ahead and stop this share, open up another document. This one should be it when it opens up. There it is. Let me expand this so we can see more of it. And I will share this document with you as well. Okay, here we go. This is what next semester schedule is going to look like. After you finish the ESYS 50 course, you have the entire ESYS catalog available to you. 55 microcontrollers, industrial, Internet of Things is available to us on Monday nights. On Tuesday nights, we have the CAS 83, which is Computer Essentials. This is equivalent to our ESYS 63. CAS 83 and ESYS 63 are the same course. We offer the CAS version under Computer Applied Science during the spring, and in the fall we offer the ESYS label, which is ESYS 63. It's the same course, the same content. And that's offered on Tuesday night in the spring, or you can wait until fall of next year to take the courses under the ESYS label. Now, on Wednesday night, we have the ESYS 51 course, which runs half a semester. It is being taught by Professor Phillips. It's a fun course, but it is half a semester, so it runs first half January 19th up through March the 12th. And then there's nothing after that particular half semester is done. The alternative to ESYS 51, because you don't have to take things in sequence, 51 is also going to be offered in the fall. 51 is something that we like to offer every semester. So if you don't take it next semester, you can take 51 in the fall. But what's exciting about Wednesday night is a new course, the ESYS 69. The ESYS 69 is teaching our students about industrial motors. And there's an enhancement that I'm looking for the dean's approval to add to 69, and that is the robotics content for industrial control. So we already have content that's planned for ESYS 69. It is a full semester course. It finishes at 8:50, 9 o'clock in the evening, as your class schedule does now, starts at 6 o'clock, and a really fun hand-filled lots of things to do type course. Now, with what the dean may be approving, and hopefully she does soon, would be this enhancement to the ESYS 69 course. So let me look that up for you. So ESYS 69, if the dean approves the acquisition of this robot arm, You may have seen images of this robot arm used in manufacture. If you take a look at any type of videos of robotics with respect to our friends Tesla, right down the street in Fremont, right down the highway, they use robot arms by FANUC all over the place. All aspects of welding are done with robots. All aspects of manipulating parts, assembling parts are done with robots. And so if we can get this in to be added to the 69 course, the exciting thing here is this has never been offered before at Chabot, and it will result in at least one certification and can result in a second certification. So we would be using the curriculum for this robot arm in conjunction with our motor controls, and I'll talk more about these and give you more detail come Monday next week when we meet face to face. But the exciting thing about this is we're gonna, if we can get this in for the spring, it'll only be offered during the spring. It will not be offered in the fall on Wednesday nights. So the choice is, do you take 51 for 8 weeks, or do you take this for the full semester and be able to earn up to 2 certificates on the robot arm for this particular course? Really, really exciting. So one of the certificates will be the successful completion of the course. So that will be a certificate that has FANUC's logo on it. And then there's a separate certificate that is available by our students taking an industry examination. And that industry examination is done under the auspices, if you look at this page, NOCTI FANUC certification. This is a worldwide recognized certification for the entry level of understanding how to control and manipulate the robot. And this will give you a tremendous edge in terms of higher ability, being trained as an apprentice, being trained in any aspect of manufacturing. Tesla is only one example that uses a lot of these machines all over their Fremont facility. So very, very exciting. I will keep everybody posted. If we don't get this in, we still have a very exciting motor controls course that is in very high demand in the industry. That is the ESYS 69 on Wednesday night. But if I can get this in addition to the motor controls, then we really have a lot of sizzle to the steak, so to speak. Okay, and so we'll give you more information on these come Monday. But here's a picture in the lower left that shows the cage in which the robot arm is housed, and then the controller, and then what's shown in the middle of the handout is the handheld touchscreen controller that is used by students. Students will be trained on how to use this. This is the same controller that is being used at various places within the facility at Tesla, where the actual factory workers are controlling the robotics using this particular controller. And the first page goes to show the scale of the size of the robot arm in the cage with people on either side. And then the middle image goes to show the specific robot arm that we will be working with. So that's what's happening with respect to Wednesday nights for the semester forthcoming. Any questions there for now? Okay, let's go ahead, stop that share, and we'll get you more information between now and Monday. I'd like for us to take a look at Canvas. So let me go to Canvas and then we'll share that screen. In store for us for Monday will be this. That is opening up. And then go to module 13, which is next week. We're still in week 12. So why are all these open? Is it still thinking? Everything can't be open, that's silly. No, something is stuck. Well, so be it, something is stuck. I will just come down, let the screen catch up with us. week 13, week 12, and week 13. So if you take a look at week 12, we finished the lab, last week's lab, this past Monday. And so you'll upload your information that you accumulated, screenshots, things of that sort, into this week's folder, and you'll get the other 50 points for the total of 100 points on the lab. There are some additional things for you to be playing with, but take a look here. Notice in week 12, I do have week 13 safety presentation, week 13 soldering video guides, week 13 soldering homework questions, GFCI notes. So in preparation for Monday, our job Monday, one of the things that we will be doing is we will be going into this room 1616 lab, and we will be soldering. We will be making an electronic project. And how many of you have never soldered before? Raise your hand. Weiji, you've soldered before?
Yeah, on the 51 course.
Okay, of course, yes. All right, so you went through that. Jacqueline, have you soldered before?
I have after school programs.
Oh, nice, fantastic. All right, Yusuf, have you soldered before?
Guitar and speaker work.
Oh, fantastic. Okay, and Brad, have you soldered before?
Yes, I have for my job. One day I was helping the electricians out. They're doing some of that.
This is great. Everybody's got soldering experience. All right, that'll make part of our Monday lab very, very expeditious. So what is needed for us to do before Monday, this is essential, is to view the safety presentation, view your soldering video guides. And if I open this up, you can see in here, there happens to be 2 YouTubes that present information on how to solder safely, how to solder correctly, and whatever experience you've had before, that's great. We commend you for having a level of preparation that most people in 50 don't have already. So this is good, but this may be good review for you, and I'm sure some of the content you may not have seen before, so you'll probably learn some new things by viewing the video guides as well. Now, in addition to that, we do have a safety presentation that has to be viewed. It's a PowerPoint, and I will be loading up a safety test, safety quiz that everybody must take. Weiji doesn't have to take this because he's already taken 51, which is our fabrication course, so he's already passed that safety quiz, but everybody else will need to do the safety quiz based on this presentation. And the safety presentation is a PowerPoint, it's available in PDF. There's 3 files in here, but they're the same content. So you can open up whichever format is easier for you to use. Some people have asked for this in PDF because they're using Apple's. And the rest of us can use PDF, PowerPoint by Microsoft. So if I open this particular guy, you'll see that there's 32 slides, and they're not hard to go through. So you'll go through reading the 32 pages, and based on those 32 pages, you should be able to take the safety quiz, pass the safety quiz with a passing score, and pardon me, then everything will be ready for our work on Monday to begin for a soldering exercise. Then, let's see, what else do we have for Monday? We'll let Canvas catch up with us in a moment. So while Canvas is catching up, by raise of hands, how many of you have had a chance to get started on the voltage divider homework? I know Jacqueline has, she's asked me a question on that already. Brad and Yusuf, Mttg, have you had a chance to start on the voltage divider stuff?
No, I'm sorry.
Okay. I will be talking more about that, so it will be helpful for you to be engaged with calculator in hand as I work through some examples with you. All right, so back on Canvas, you'll see the last thing that's part of week 12. That is a week 13 soldering homework questions. This has to be completed. And it is a questionnaire that you can fill in based on the resource of the videos and additional content that I will be supplying to you all. And it's opening up. I think it's 1.5 pages of fill-ins, and there's a Canvas upload for this. So we just want to make sure that you have viewed the videos and can answer the questions competently so that when we actually get into the lab, you will be working with the lab in as safe a manner as possible, and after having been thoroughly prepared with a PowerPoint presentation, with video presentation, and also with answering these questions on this homework. So everybody should be able to see the soldering exercise homework questionnaire. What is the purpose of soldering is the question number 1. What is solder and what is it made up of? What kind of compounds is it? What are the main tools that you use for soldering? Something called the soldering iron. And we talk about different tips and which has advantages. What are helping hands? What type of temperatures are we likely to get the soldering iron up to? Why should you be washing your hands after soldering? So yeah, 1.5 pages of questions, very, very important for you to complete before Monday. Okay, so this is due by Sunday midnight. Any questions about the soldering videos, soldering PowerPoint, safety PowerPoint, and also completing this questionnaire, as well as a safety quiz before Monday? Okay, pretty straightforward. Okay, so that being said, let me stop the share on this. So we were able to cover our schedule for spring, able to cover the introduction to the soldering exercises. Let's move into some of these voltage divider exercises and make sure you've got a comfort level in working with those. So let me go ahead and get a page out for focus. Let me change the view to camera mode. Thank you for the reminder. All right, so we're discussing voltage divider circuits, and here's an example that's not dissimilar to something that you have set up in one of our homework exercises. 15-volt source, R1, R2 form the divider network to which a load is attached. What is a load? A load is any device that draws electricity to work. This could be a fan, this could be a motor, this could be a lamp, it could be a simple resistor. Whatever it is, we do have a specification that it requires 8 volts and it requires 30 milliamps in order for this to work. So this is attached to ground. We have a ground attached here. This is our circuit. My recommendation, regardless of how your homework specifies which answers the homework is asking for, is for each one of these, set up a very simple VIR table, VIR. You have your R1, R2, which is your divider network. Then you want to account for your loads. So we happen to have a load here. So it's an RL and then a row for totals. So we have 3 columns, 4 rows, a total of 12 cells in order for us to fill in. Your homework exercises might ask for 2 values, might ask for 3 or 4 values. We're going to go for the gusto and make sure we review the proper use of our VIR tables, analyzing what's going on. So the first question went out to your classmate, Brad, and the question was, where do we begin? And he suggested, well, we should do, we see 15 volts as a source. We should recognize that 15 volts is the total and it should go in this particular cell. So my next question is to Yusuf. So Yusuf, what would be the next thing that you would fill in?
The voltage across the 2 resistors in series.
The voltage across the 2 resistors in series, because I have R1, technically, they form a voltage divider. Technically, they're not in series with each other. They look like they can be. If I remove the load, then clearly R1 and R2 are in series. But because I have a load coming out here, I have a split of current. So series means that the R1, R2 would be same current, but I clearly don't have the same current between going through R1 and R2 because there's a split here. So perhaps you want to rephrase what you want to fill in the chart. Yusuf.
I don't know really.
Okay. Let's give Jackie, what would you do?
Fill in 8 votes for our load resistor.
Precisely, because we said this thing that attaches over here is a load. If this is attached to your divider network. So R1 and R2 form a divider network. They're not in series with each other, but they do form a voltage divider network. And we have this thing attached over here. This is another device. It's called a load. And therefore, we have accounted a separate row for our load, because with this, we can determine some information. So Jackie says we should be able to, since we're given 8 volts is required by the load, so you want me to write 8 volts in this cell, is that correct, Jackie? All right, so 8 volts goes here. Very good. All right, so the next thing, Wei Ji, what would you suggest would be another cell we could fill in?
Since R low and R2 is parallel, so R2 gonna be the same voltage. So we fill in R2 with 8 volts too.
Okay, so what your classmate, what Wei Ji had said was this load resistor, which is shown simply as a rectangle, this load resistor is in parallel with R2. They are connected at the top, and separately they are connected at the bottom. So if devices are connected to a common point on one side of their devices and connected to a different common point on the bottom of their devices, then R2 and this load must be in parallel with each other. Recognizing that these are in parallel with each other, what is the same in parallel circuits? We remember that voltage is the same. So if I have 8 volts across my load resistor, here I have 8 volts, and R2 is in parallel with this, it must also share the same voltage. So Wei Ji is suggesting that we put 8 volts in this cell, is that correct? 8 volts. Okay, that's another piece of the puzzle. So far, so good. Now, Brad, back to you. What would you do next? Is there any other piece of information we can put in here? We already put that on the table. We already put that on the table. What else?
The current.
Okay, the current of 30 milliamps. And this current of 30 milliamps goes where in this table?
It goes for the load.
Yeah, it goes in the current column right here.
Yeah.
And it is associated with the load because that's one of the requirements. So that 30 milliamps has to be right here. Done. Wow. So out of 12, we've already been able to fill in 1/3. So we have a little ways further to go. What would be the next thing that we could determine in this exercise? Yusuf, your turn.
Use Ohm's law to calculate the resistance on the load.
Okay, we can use Ohm's law to calculate the resistance on the load. And just as a reminder, V, I, R. So if we're looking for the R, it would be V divided by I. So which V divided by which I, Yusuf?
8 volts divided by 30 milliamps.
Okay, so let's go ahead and take 8 and divide by 30, exponent, change sign 3. And your calculation works out to be what, sir?
266.66 ohms.
And let's see, put this in engineering mode. And yes, I concur that we have 266.67 ohms, yes? 266.67 ohms. So far, so good. All right, Next, Jacqueline, what would you do next? We have a few more to fill in. What do you think?
The first resistor's voltage.
Oh, and how would you determine the first resistor's voltage? We have nothing on that row. We don't have the ohms, we don't have the I. How do I determine that voltage?
Subtraction. 15 volts from the source minus 8 volts.
Precisely. Because if you look at the left side of the circuit, do you see a 15-volt source, my friends? Isn't the 15-volt source right here attached to ground? Yes or no? Ground is here, ground is here, ground is here. It's attached to ground. So that means if I measure from the tippy top right here, if I were to call this point A, and I were to measure this with a red probe, and I put my black probe, put a black probe on ground right there, I'm going to measure 15 volts, yes? Well, suppose I move my red probe over here to the top of R1. Isn't the top of R1, isn't this point also a point A? There's no resistor between them, it's just a piece of wire. So this is a point A, this is also point A. So my 15 volts can be realized here. Voltage at A is plus 15V. Over here, my voltage at A is equal to plus 15V. My red probe is at the top of R1. My red probe is at the top of the voltage source. They're going to measure with respect to ground, positive 15. Now, I'm going to move my ground pin from here to my black probe to here. So that means from A to ground, meaning across R1 and R2, I have a combined how much voltage? 15 volts. How much do I have dropping across this load resistor and R2? I happen to have, let's see, call this point B. The voltage at point B at this point measured to ground is 8 volts. So I have from point B to ground 8 volts because that was a demand of the load. And I have at point A measured to ground a source of 15. So if you take a look at R1, R1 has potential on the top of positive 15 volts. R1 has potential at the bottom of R1 at positive 8 volts. If these are not at the same potential, then there must be a voltage between them. What, if you recall, what was one of the definitions of voltage? Wasn't one of the definitions of voltage a difference of potential? In other words, a difference of charge. Charge is the same as potential, difference of charge between 2 points. That's one of the definitions of voltage. And clearly, at the top of R1, we have charge. We have potential of plus 15. At point B, the bottom of R1, we have a difference of potential of 8. So voltage as defined as a difference means, Jackie is right, we're going to subtract. 15 will subtract the 8. So therefore, how much voltage will be across R1? 15 subtract 8 will give us what, Jackie?
7 volts.
7 volts. So we will write 7 volts right there. So I just verbalized for you all a reminder, a reiteration of how we justify calculating 7 volts here. Okay. All right. This is very good. We're making great progress. So the next question goes to Wei Ji. What would you do next? We have 4 more cells to fill in.
No idea yet.
Okay, well, if you remember from Monday, if you had a chance to review Monday's video, because I posted that actually Monday evening, we went through analyzing voltage divider circuits. And there is something known as bleeder current and something known as a bleeder resistor. A bleeder resistor. And in the design of voltage divider circuits, whatever is the last resistor in parallel with the last load, the smallest demand load, whatever resistor is in parallel with the smallest demand load will be the bleeder resistor. So this is RB, RBL, the bleeder resistor equals RBL. So R2 is the bleeder resistor. Once we identify the bleeder resistor, then bleeder current will in design, your I bleeder is equal to 1/10 of your load currents. 1/10 of your load currents. Do I have a load current? Wei-Ji.
Yes.
And what's 1/10 of this load current?
3 milliamp.
Precisely. So electrons, and I'm going to put in the polarity, electrons are flowing here, they're flowing down. They're flowing over here. And as they flow in this direction, there's two paths. One path coming up through the load resistor, one coming up through the bleeder resistor, and then they will meet right here, continue through the first resistor, and continue this way, and ultimately back to the source. So this is how the currents will flow, like so. Current electrons will leave here, come here, and then the electrons will split. Some will come up through R2, some will come up through the load resistor. So in design, when we're dealing with designing a good voltage divider circuit, the rule was that the bleeder current should be 1/10 of your total load currents. You're given one load, your load current is given as 30 milliamps, 1/10 of that is 3 milliamps. So your IBL in this case is equal to 3 milliamps. Does everybody understand how that calculates to be 3 milliamps? It's got to be 1/10 of your load current. Everybody okay with that? So once you identify 3 milliamps and it's flowing up through R2, can we fill that in a cell right here? 3 milliamps, like that. And that's what we would do. Okay, Wei-Ji? That was part of Monday's lecture and Monday's video. So please do review that in addition to this afternoon's video. All right, so far so good. Now, Brad, do we have enough information now on the table to fill in one more cell? Couple more cells? What do you think? There's a lot of different ways we do different things.
I think we can do R for resistor 2, right? Because they're parallel to each other.
Well, you can calculate the ohms for R2. You can calculate the ohms for R2 just by using Ohm's law. The parallel relationship dictated that both the load resistor and R2 were 8 volts. That's how the parallel relationship helped us out. But once we've identified this as 8 volts, then we don't rely on parallel to determine this guy. We determine this guy by using Ohm's law. Okay, so if I cover up the R, my R will be calculated as what? V divided by I. So we're going to take the 8 volts and divide by 3 milliamps. And what do you calculate, sir?
I got 2.6 milliamps.
So 2.6 what? There's 2 digits after the decimal point.
2.67, I'm sorry.
Okay,
Milliamps.
precisely. So you would calculate 2.67 K ohms.
Yeah, I'm sorry. 2.67.
Okay,
kilo
it should be, yeah, that's a kilo. That's not a milli. That's a +3, not a -3. So 2.67 kilo ohms. And resistance is measured in ohms. We use milliamps in order to calculate ohms. Okay, so now we have 4 more cells to fill in. So far, so good. Yusuf, what would you do next? You're a detective. As a detective, you're going to use deductive reasoning. Deductive reasoning. What deductive reasoning means is take what you see, what you observe, take what you know, and figure out what you don't know.
The current across R1
The current through.
through R1.
Okay, yeah, because voltage is across a device, current goes through. How do you determine the current through R1?
Well, the current had to split in order to get to R2 and the load. So if we add it together,
Ah, okay, so what do you calculate that to be?
33 milliamps.
All right, so take a look at my schematic. You're entirely correct. If you've watched how I've drawn the arrows for current flow, the electrons leave the negative plate, come down here, flow here, they split. Some of it goes up through R2, some of it comes up through the load resistor. How much comes up through the load resistor is 30 milliamps. We have that written. How much comes up through the bleeder resistor was based on our formula, 1/10 of load currents. So I have 3 milliamps here. 3 milliamps going up, 30 milliamps. What happens at node B? Don't they combine? So that they combine to give us 33 milliamps going through R1. Does everybody see how that combines to add up the 33 milliamps? So far, so good. So we will have 33 milliamps going there. Excellent. Now, we have 3 more cells to fill in. Jackie, what would you do next?
I would find the resistance of R1.
Sure. And how would we find, what method do we use?
V over I.
V over I. So let's go ahead, Ohm's law. Take the V of 7 and divide by the I of 33 milli. And what do you calculate?
212.12 ohms.
212.12 ohms. 212.12 omegas. And that would be correct. We just proved it on this calculator as well. All right, Wei Ji, bring us home. We have 2 more cells to fill in. How do I do this? I can't
Calculate the R total.
So what do I do?
So, R2 is parallel with R load, so we use the reciprocal formula to calculate the
In equivalent resistance. We could certainly do that. We can determine that since R2 is 2.67 k ohms and the load is 266.67 ohms, we can calculate these 2 guys in parallel with each other to give us these 2 combined. And then what?
And then we add with R1.
And add that with R1 of 212. So yes, we could do that. Why don't we try that? The 266.67 reciprocal plus 2.67 kilo reciprocal equals. So these 2 in parallel combine to give us 242.45. And we're going to add that to 212.12. And what do you get, sir? What do you calculate, Wei Ji?
454.57 ohms.
And here, oops, did that too fast. So let me take your number.
454.57 ohms.
454.57 ohms. Okay, so we can very quickly confirm that. So 266.67 and hit my reciprocal key and then plus 2670 reciprocal equals, and then now add 212.12 and engineering 454.57 ohms. So this works out well. And then from there, we can calculate current, yes? I would submit an alternative method. Oops, what happened to my camera? It disappeared. Oh dear. Hang tight. It'll come back. There we are.
I can still see the camera.
Okay, I lost it for a moment. Thank you. All right. So I would submit an alternative method. That was a bit of work, calculating these in parallel with each other to a single equivalent to be added to R1 to give us this total. That works fine. But hopefully you would have realized this. The current that came out of the source at the bottom of the circuit came this way and split, and then they recombined to 33 milliamps going back to the source. Don't you have the current going back to the source as 33 milliamps? Isn't that something we should recognize, that the current through R1 is in fact the total current? Okay, that should be a recognition, not a calculation. So we should have 33 milliamps right here just by these two currents combining to give us the current through IR1, which is the total current. Once we have this, can we use Ohm's law to simply calculate ohms? That's why I drew a diagonal. The first value above the diagonal was calculated using parallel and in series addition. This lower part of the diagonal will be calculated using Ohm's law, because the 33 milliamps should be recognized. And let's go ahead and do that. Everybody take 15 volts and divide by 33 milliamps. I'm going to key that in as 0.033 just to make it easier. And you end up calculating what value, Yusuf?
454.55.
And that works out to be 454.55 ohms. And yes, we could be 2/100ths of a decimal point off and be very happy with this result, because remember, we were using rounded off values in here for calculating ohms. This would be a very good method that would help you understand all of what's happening in voltage divider circuit design, and by doing a complete VIR analysis with a simple table in this fashion, okay? And although the exercise only asks for 1 or 2 answers or 2 or 3 answers, this is a more thorough analysis that will march you very successfully towards our final exam. Any questions about this particular example? Okay, let me move on to another example. And here, let's see, we're gonna do this guy this way. I'll have a voltage source, and this will be a 70 volt voltage source. I will have a resistor here, a node, a resistor here, and I am going to attach, let's see, a load resistor here and here. And this load will demand, let's see, 27 volts, and it will demand 25 milliamps. And this will be my R1, and this will be my R2. And in the homework exercise, you're presented with a circuit similar to this. You're asked for current through R1, the current through R2. You're asked for the ohms of R1, you're asked for the ohms of R2. So you only asked for 4 things, but what was my recommendation for you when you're faced with something like this? Is let's go ahead and go back to do our friend, the VIR analysis table. So we have R1, R2, there is a load resistor, so RL and total. And separate our columns this way for V, I, and R. Okay. let's go through a bunch of steps here. Brad, give me something to fill in.
We can fill in the voltage total since that's what we have.
Okay, we'll fill in the voltage total. All right, Yusuf, give me something else to fill in.
The voltage across the load,
Voltage across the load, and that's given as?
27 volts.
So here's the load, so 27 volts. All right, and Jackie, give me something else to fill in.
The current through the load.
Current through the load is specified as 25 milliamps. Cool. All right, Wei Ji, give me something else to fill in.
We calculate the resistance of the load.
And calculate the resistance of the load. So everybody use Ohm's law, yes? 27 divided by 25 milliamps. And I'm going to code that in as 27 divided by 0.025. That's my 25 milliamps in decimal. And what do you calculate there, sir?
1.08 ohm.
So we have-
Kilo.
Yeah, 1.08 kilo ohms. Everybody okay with that? 1.08 kilo ohms. So far, so good. Brad, you're up. What could you do next?
It's the milliamps for the RL will be the same for R1.
The milliamps would be the same. Why would the current be the same?
No, I'm sorry, not the current, the voltage,
Oh, and why would the voltage be the same?
because let's see, because they're both connected by that point on the top, right?
Mm-hmm. The top of these are connected at that point up there, which we will call A. And what?
And voltage in parallel is, when they're in parallel, is the same, right?
Okay, so you're saying that R1 and this load resistor, because this will be an RL, that R1 and RL are in parallel to each other. That's what you're saying?
Yeah.
Okay, because the wire at the top of these devices is connected to point A, and the wire at the bottom of these devices is connected to a different common point. Yes, these are in parallel with each other. So as they're in parallel with each other, you know that voltage is the same across branches of a parallel circuit. So you're saying we have how much voltage across R1?
27 volts.
So we write 27 volts right here. Okay, very good. Step by step, that's good. So Yusuf, what would you find out next?
We're going to do our bleeder resistor step.
Okay, so the bleeder resistor step. So your I bleeder. So how do we find I bleeder?
It's R1 because it's in parallel with our load.
It's in parallel with our load. So how do I find the value of this current?
So it's equal to 1/10 of the current going to the load.
Okay, it's equal to 1/10 of your load currents. And so in this case, it is 1/10 of 25 milliamps, which calculates to be
2.5 milliamps.
2.5 milliamps. And that was a design rule, yes, everybody? So we have the bleeder is in parallel with the load, and this works out to be 2.5 milliamps. So at this point, what I'd like to do is put in polarities, and let's draw how the currents are working their way through this circuit. The top of the voltage source is what polarity? Class?
Positive.
Positive. The bottom of the voltage source is
Negatory.
negative. And the electrons leave which plate of the voltage source?
Negative.
Negative, correct. So they will come down, flow to the right, come up, and then once it hits node B, what happens to this current? It will
Split.
split. Part of this will go to the right, part of this will continue up. So we happen to have a split right here. We know, or we're given, how much current flows through this leg. So we have 25 milliamps flowing through this leg. We just determined that your bleeder resistor is the resistor, last resistor of the smallest load. There's only one load. This is in parallel with it. So this is R1 is the bleeder resistor. And as the bleeder resistor, the current is determined by rule for the proper design, 1/10 of total load currents. So we calculated 2.5 milliamps going up through R1. And we have 25 milliamps coming in through the load, meeting at point A. So what would be the next step of what you would determine, Jackie?
The current through R2.
The current through R2. And how would you determine the current through R2?
You would add the currents through R1 and the load.
Okay. So if we take a look at this, don't these two currents combine at the very top? Don't they combine to go back to the source? And isn't this current that flows back to the source the sum of 2.5 milliamps plus the 25 milliamps? So how much current do I have going back to the source, Jackie?
You have 27.5 milliamps.
27.5 milliamps. So if this is going back to the source, isn't this also the current coming out of the source? 27.5 milliamps. And isn't this current the same current that is flowing through R2? Because it doesn't split before R2, the current splits after R2. So we know that IR2 must also be 27.5 milliamps. 27.5 milliamps. So that's what helps us fill in that particular cell. Can we fill in anything else at this very same moment, Jackie?
We could fill in the voltage for R2.
No, let's stay with currents.
No? Oh, total current.
We can fill in total current, can we not? Remember, the current that goes back to the source, the current that comes out of the source is total current. And by virtue of analyzing all of these currents as they flow with these arrows, when these two currents combined at the top at point A to go give us 27.5 milliamps going into the source, that is your total current. Anytime you can fill in currents, and currents are one of the easiest things to fill in when we're doing circuit analysis, fill in that column first, okay? All right, so good job. We filled in the entire current column. So Weiji, what would you do next?
R2, the voltage of the R2.
Voltage across R2. Well, you can't calculate this using Ohm's law because we're missing two cells here. We can find the ohms here because we have two in order to calculate ohms. So how do I find this if I've got two things missing on that row?
We use 27 divided by 2.5. You mean how do we calculate the real?
How do I find this voltage here? Yeah.
So we use the 70 minus 27.
Ah, okay, because our source from here to here is 70, yes? From here to here is 70. Isn't that from point A to the bottom of R2? Isn't that across two resistors? And one of those resistors is going to drop 27. So if you start off with a total of 70 between here and here, and we lose 27 between here and here, then you're going to use the subtraction method to find out what's left across R2. It will be the 70 subtract the 27 that will be remaining across R2. And what value do you calculate there?
43 volts.
Okay, so that's 43 volts. Is everybody okay with how that 43 volts is determined? So far, so good? Okay, now the rest of this is academic. This is just Ohm's law, yes? So let's go ahead and finish this up. Brad, can you give us the value of R1, please?
Yeah, so for R1, I calculated 10.8 kilo ohms.
So that works out to be correct, 10.8 kilo ohms. And Yusuf, the value of R2,
1.56 kilo ohms.
so it works out to be 1.56 kilo ohms. And how about the total ohms there, Jackie?
2.55 kilo ohms.
70 divided by 0.0275. So 2.55, yes, 2.55 kilo ohms. Okay, is everybody all right with how to analyze a voltage divider of this sort? So far, so good? Okay, and let's see. We will do a different analysis. We may jump back to voltage divider in a moment, but let's take a look at a different analysis, and this would come from our circuit. So this will be an RL circuit. Let's see, no, we'll stay with RC. So stay with RC circuit. And the RC circuit showed a AC source, and it showed a capacitor, and it showed a resistor. And let's say this particular circuit has C equals number 783. So based on this having a C of 783, you are tasked with finding the value of C. How do we go about finding the value of C if you're told that C is equal to a number 783? So the question goes, Yusuf, do you remember?
First digit is 7, second digit is 8,
First digit's a 7, and the second digit is an 8.
followed by 3 zeros.
Followed by 3 zeros. Anything else? Is the capacitor?
Picofarads.
What's that?
Picofarads?
We have to write down picofarads. Okay. Now that's way too many digits for us to deal with. So can we simplify this to enter proper engineering notation into the calculator?
78 microfarads?
No, if you key this into your calculator at 78 nanofarad.
No.
Okay, so we'll prove it to yourselves. You take 78,000, there's your 78,000, and then you key in pico by exponent negative 12. So pico is exponent negative 12. And so if you hit equals on here and engineering, it works out to be 78 10 exponent negative 9 nanofarads. Now, 78 nanofarads. If we had to specify this according to the way the world standardizes capacitor values, how would we change our answer? Because 78 nano is what we calculate for proper engineering notation, but the world does not use nanofarads as a standard measure of capacitors. Standard measure of capacitors are farads, microfarads, or picofarads. So what do I need to do to get this into proper notation for the rest of the world? Question goes to Jackie.
Change it to microfarads.
Change this to
0.078
microfarads. And on your calculator, since you've calculated, we keyed in 78,000 pico, and we hit equals, and your calculator displayed 78 nano. If I hit the engineering key one time, let's see, will it go in the other direction? No, it does not go in the other direction, unfortunately. So it does work out to be 0.078 microfarads. From here, yeah, we would move the decimal point 3 places. This would be nanofarads in this position. Move the decimal point another 3 places. Then this would be microfarads, 0.078 microfarads. So this is the standard that the world is looking for. For our calculation exercises, we can just use 78 nano. Now, so capacitor calculates at 0.078 microfarads. If I were to give you a frequency, okay, if I were to give you F is equal to 475 hertz, and your VS is equal to, let's say, 10 VRMS. Do I have enough information to determine the next piece of our work? And that would be XC. And how would I determine the value of X sub C? Wei G?
1 divided by 2 pi FC.
1 divided by 2 pi FC. And this would be equal to 1 over 2 times pi, and the frequency is times 475 times the C value, 78 nanofarads. How would I key all of this into my calculator? The way I would key all of this into my calculator is start by calculating the denominator and then reciprocate it into 1. So this calculation, the keystroke sequence, should look like this. 2 times your pi key times 475 times 78 exponent -9 equals, then followed by reciprocal, and then followed by equals. Actually, on your calculator, I think there's one more step. On your calculator, if you're using our $8.98 special, there's one more step, and you have to hit shift right here. So 2 times shift pi, because where's your pi key on this calculator? Your pi key on on this particular calculator is a second function above your EXP key. So in order for you to engage that second function, you have to hit your shift button, then engage this button in order to get to pi, okay? So if you use this keystroke sequence, what do you calculate the ohms of this to be? Wei Ji?
4.3 kilo ohms.
4.3 kilo ohms exactly?
So I rounded.
4.3 kilo ohms. Let's try that, and let's do this together. 2 times shift pi times 475 times 78 exponent -9 equals, and then reciprocate, and then equals. So as you round this, and I would concur with you, works out to be 4.30 kilo ohms. Is everybody okay with X sub C? So far, so good? All right. Now, I'm going to give you an R. R is equal to, blue, VIO, red, SIL, at max tolerance. And yes, you'll be seeing stuff like this during our final. You'll be getting a capacitor code. You'll need to accurately determine the capacitance. You'll need to determine what the reactance is. You'll be given color codes at minimum or maximum tolerance. You'll need to interpret this in terms of resistor value. So the question now comes to Brad, your turn. How do I decode this to determine the value of my resistor?
So that's a 4-band resistor. So the first color, the blue will be the first digit. That's 6.
Okay, so we have a 6 followed by?
Followed by a 7.
Followed by a 7.
And then the third digit number is zeros. Red is 2 zeros.
2 zeros. Followed
And
by?
Followed by omega.
Omega, correct. Followed by?
10% plus or what's max.
Plus or minus 10%. Okay, so we write down this first. Now we have to determine this at maximum. So what decimal multiplier am I going to use to determine this at maximum?
What was the question again? I'm sorry.
How do I determine maximum? I'm going to multiply this by some kind of a decimal.
6,700 ohms times 1.1.
1.1 would give us maximum tolerance for this. So I multiply this by 1.1. So that's equal to R. And so R calculates to be what value on your calculator, Brad?
7.37 kilo ohms.
7.37 kilo ohms, yes? Okay, so now we have an R value, that's 7.37 kilo ohms. Now, how do I determine the next things, because there's total current involved with all of this also. So how do I find the currents that are going through each of these branches? Question would then go to Yusuf. How would I find the current going through each of these branches?
I guess we can calculate the current going through the resistor with Ohm's law.
Okay, so we're going to rely on Ohm's law, and I'm going to rewrite Ohm's law slightly. We already know it's V, I, and we've always written R in this corner, but because we're dealing with a number of new quantities, I will write VI omega. And omega could represent R, or it could represent X sub C, or it could represent X sub L, or it could represent Z. Any of those four quantities are measured in ohms. So we'll use Ohm's law and call this VI ohm instead of just VIR. But since we happen to be asking for some currents, Yusuf says we should be able to calculate a current going through here. So this will be my IR. How would you find the value of IR, Yusuf? You said Ohm's law.
10 volts divided by the resistance we calculated, 7.37 kilo ohms.
7.37 k ohms. So where did the 10 volts come from?
Our voltage source?
Our voltage source is given as 10 volts. And what is the physical relationship between capacitor, resistor, and the voltage sources? They are in parallel with each other. So we know that if I have a 10 volt source here, I must have 10 volts across the cap. I must have 10 volts across the resistor. So based on that, can I calculate the current? So 10 volts RMS divided by 7.37 k ohms, which we calculated earlier. Let's go ahead and do that. 10 divided by 7.37 kilo. What do you calculate that current to be, sir?
1.36 micro ohms, like microamps, milliamps.
Well, is it microamps or milliamps? Which
It's
is
milli. It's milli.
okay. It's 1.36 milliamps RMS. Okay, everybody concur with that calculation? So far, so good? So far, so good. Now, the next step is how do I find the value of IC? So the question goes to Jacqueline, you're up.
We would be using X sub C for our ohmic value.
Mm-hmm.
So V over.
Yeah, still V over ohms. You're correct. The I will be V over ohms, except the ohms in this particular case will not be the R. The ohms in this case will be X sub C, which we calculated earlier right here. So you are correct. It will be V over X sub C, and it would be 10 VRMS over your 4.30 kilo ohms. What current do you calculate as a result of that?
2.33 milliamps.
And yes, it does round off to be 2.33 milliamps. So 2.33 milliamps RMS. So far, so good. Now, based on this, do we have enough information? Do we have enough information to calculate I total? And this is what I haven't shown you yet, how to calculate I total for a parallel RC circuit. But let's see if someone can noodle this out. Mr. Weiji, do you think you can figure this out for us? We have a current that flows through the cap, and
Just
the
add
cap
them
current,
together.
2.33 milliamps, and we have the IR at 1.36 milliamps, and they come together and they give you a total. So instinctively, similar to what we've done in the earlier voltage divider circuit, when currents come together, you add them to give you a total. These guys, instinctively, looks like you would add the 2.33 plus the 1.36 to give you a total. However, this is an AC circuit, and we have a capacitor, which changes our timing quite a bit. Remember, in a capacitor, we have to think about Eli the Iceman. We have to think about current leading voltage. So what I'm saying to you is these two currents are not in phase with each other. Your IC is not in phase with your IR. Why is that? Let me show you what's going on. We said for resistors, we have this kind of a phase relationship. We have a VR moving in phase with IR. We said for capacitors, we have a different relationship. With capacitors, you want to think about ICE, because the C stands for ICE. Which quantity comes before the other? Because this is, one of these represents current, and one of these represents voltage, because the E and the V represent voltage. Which one comes first? In the case of capacitors, because of RC time constants, the current comes first. So that means my IC will already be pointing in that direction by the time VC happens. This is the phase relationship with respect to capacitors. They're not in phase with each other as these guys are. So here's the key. When I'm dealing with series circuits, if I'm dealing with series circuits, what is the same in series circuits? What is the same in series circuits is current is same in series circuits. So that means when I combine this set of phasors with this set of phasors, I have to align my red phasors in the same direction, because why? Current is the same. So when I put these together, watch what happens. I have an R that has to go along with a VR, but I have to align it with IC. So if IC is rotated to point at 0, if I rotate this in this direction, where is VC forced to rotate? Because I have to maintain 90 degrees here. My VC is forced to rotate in this direction. I now have two sets of phasors combined. I'm combining the resistor phasors with my cap phasors, and in series circuits, I have to align the currents. If I align the currents, they are the same. They will cancel, listen carefully, they will cancel in the phasor diagram. What this leaves me with is VR is at 0 degrees, whereas my VC is at negative 90 degrees. When we put this together in the form of a Pythagorean triangle, we end up with, we start with VR. So here's my VR. I'll do this in green. VR at 0 degrees. And at the very end of VR, I will then attach my VC at negative 90 degrees in order to find my V total right here, and my angle is going to be a negative phase angle coming down, and we calculate this using Pythagorean theorem. That's what happens in series circuits. We've done this for a couple of weeks now. With parallel circuits, what is the same in parallel circuits? Current's not the same. What is the same in parallel circuits? Voltage. Oh, come on. Running out of purple. Voltage is same. Now, if I'm combining these phasor diagrams, if I'm combining the phasor diagram for resistors and the phasor diagrams for capacitors, and I want to keep capacitors the same, or the voltage the same, here's my VR, here's my VC, IC, and I'm going to keep VC pointing in the same direction as VR because their voltage is the same, they're in phase, which means my IC is going to be pointing up. IC. What happens, since VR and VC are the same, they cancel. What that leaves me with is this relationship. IR is pointing that way, and IC is pointing this way. Or if I do it this way, here's my IR at 0 degrees, and right here is my IC at positive 90 degrees. And what I'm finding is my I total using Pythagorean theorem. And my angle of theta in this case is a positive phase angle. So based on this, you should be able to now recognize how to combine your phasors for this exercise, and that becomes nothing more than IC pointing up of, what did we have, 2.33 milliamps? 2.33 milliamps, we're almost done, my friends. At positive 90 degrees, my IR, we calculated as 1.36 milliamps for IR at 0 degrees, and my I total, you figure out using Pythagorean theorem, and the theta you can determine by SOHCAHTOA. So that's how we would take the information of this parallel RC circuit, determine the currents, because voltage is the same. And once we determine the currents, put the currents into this diagram, where IC is out of phase from IR by 90 degrees. IC is pointing north at positive 90 of the value we calculated, IR in this value, I total Ohm's law, the Pythagorean theorem. And theta you can calculate by using SOHCAHTOA. And with that, I think we've concluded all the major hit points that will help you with your homework assignments. Are there any questions that any of you have at this moment? Okay, when questions do arise, you know you can hit me through Discord, and the only instance where I may not be answering your questions is if I am in transit driving from one location to another. But this page I will leave up, and this page is your summary of what happens in series circuits. Current is the same. We align our current phasors. In parallel, voltage is the same. We align our voltage phasors and the resulting phasors that are left. Because currents cancel out, all we have left are these voltage phasors. Because voltage is the same, voltage cancels out, all we have left are current phasors. And this is the most important summary that will help you with any of the circuits that are forthcoming. Okay, so that being said, let me go ahead and take a quick snapshot of all of us here and go to the view and gallery view. And I wish you all a wonderful weekend ahead of you. Yusuf, bring yourself a little further forward so we can see your smiling.
So dark.
It's so dark. Some people like being in the dark. Brad, bring yourself a little more forward. And
See me at
G? Okay, yeah, we can see you better now. Okay, everybody, have a great weekend. We'll see you. And do look at and think about the information for that ESYS 69 class. I will have more information for us on, hopefully by Monday, whether we're closer to getting the robotic arm. But even if we're not getting the robotic arm, the ESYS 69 stands as an outstanding industry class for motor controls. So that and soldering. We will be soldering on Monday. Okay. All right. So with that, adios. Thank you very much, guys. Good job.